All right. So, okay. So now we have some data. We have a structure. Basically, we have extracted some data knowledge from outside sources. We constructed some graph, and then we want to complete the missing links here. So in order to train a model on this, we first train these on the relations that we already see. So we've learned these embeddings, and then we remove some of the essentially edges. And then we try to predict the existence of these edges. And that's how we train these models. And then once we trained it, we will use these essentially embeddings in order to learn, in order to predict the links that are missing in our knowledge graph. So for that, in our encoder-decoder approach, we need to use some type of decoder. And there are, in general, two types of decoders that we can use. The first type is translational models, in which we are assessing the distance between two entities using some measure of distance between their embeddings. And there is a second group, which are tensor decomposition decoders, which, they're using tensor decompositions in order to learn the node and basically knowledge graph embeddings. So first of all, in translational models, we're using the distance, right? So we need to define some measure of distance. Then let's say that we define a function d that measures the distance. Then using that, we're measuring how close two different entities are. And by measuring that, we're essentially predicting how likely it is that they are connected to each other. So we have three embeddings. We have edge embedding, we have head node embedding, and we have tail node embedding. Now, what we want to do in this type of translational, essentially decoders, translational models, is that we want the head node, after translation, using the embedding for the relation, basically for the edge, we get as close as possible to the tail embedding. So they are structured such that they measure the distance between the basically translated embedding. We show that here for a ZH plus R tau, and the tail embedding ZT, right? So if two nodes are connected to each other using some relation, we say that if I translate the head node using that relation type, I will get to the tail node. So this should be as close as possible to this embedding, right? So now what we want to do is to define some model, some decoder that learns some embedding. And first we start with the most basic one, a traditional one, trans-E, which is using exactly just a vector summation in order to define the decoder. So you have ZH, R, tau, and ZT defined in some essentially vector space. And then we say that in this vector space, we can just add a vector, basically embedding of the relation to the head embedding and get to the tail embedding. So if this edge exists, we want our decoder give us a basically score the plausibility of the existence of this thing, right? So we formulate our trans-E as a distance between these just vector summations, right? So we say that we translate ZH to R tau. We want that to be as close as possible to ZT. We just use, basically, we subtract that from this, and We want to, using that, get a score that shows how likely this is to be, basically how likely these two are to be connected to each other. So let's see if this trans-E method can represent different logical patterns on our relations. So for symmetry, what it means is that if I have a ZH and it is connected with essentially some H-type tau to a representation ZT here, I should be able to also connect ZT with the same relation type to ZH, right? So I write that as ZH plus R tau is equal to ZT, and ZT plus R tau is equal to ZH, right? So from these two equations, I conclude that R tau should be 0. And if R tau is equal to 0, means that these 2 points will overlap. If those 2 points overlap, that means that they have the same entity. So it cannot basically represent a symmetric relationship because we don't want those two nodes have the same entities. So same essentially embeddings, different two nodes, we don't want them to have the same embeddings. We then look if we can represent anti-symmetry. We see that yes, we can represent that because if we have a ZH, we translate that using embedding R tau to point ZT, and then we take our ZT, translate that using embedding R tau, we get to a point which is not ZH. So we are able to represent anti-symmetry using this model. Now we look at inverse. We see, let's see if we can represent inverse. So it means that if ZH is connected to ZT using some relation type tau 1, it also, ZT should be connected to ZH with relationship tau 2. So I can write that as ZH translates, R tau 1 translates ZH to ZT, and then R tau 2 translates ZT to ZH. So I take this and I conclude that if these two vectors are of the same size but in the negative directions, I have node entity, basically entity embeddings that are not overlapping, and I have unique vectors representing basically different type of relations. So I'm able to represent inverse logical pattern using trans-E. Lastly, I'm going to look at compositionality. I say that I should be able to translate Zi. So let's say that I have 3 nodes, Zi, Zj, and Zk. I learn embeddings for those, and I say that if Zi is related to Zj using type 1 and Zj is connected to Zk using type 2, I want Zi to be connected to Zk using type 3, right? So I write these equations as translations in this embedding space. And from that, I conclude that if, yes, I can represent that. If my vector R tau 1 summed with R tau 2 give me the embedding for the relation type tau 3, right? So then I can represent that. That's fine. We can represent 3 out of 4 logical patterns that we want using trans-E. Now, there are multiple approaches that have improved trans-E. They are usually represented with different trans-R, trans-X, trans-H, and so on and so forth. In general, so I'm gonna only look at trans-R, which is a prominent approach, where the intuition behind trans-R is that each entity has different, essentially, aspects. So you have a person that has basically different aspects to it, and it has different relations with different other entities based off of different aspects of it, right? So that means that we don't use the same embedding space for different relation types. We use different vector spaces to translate basically embeddings in basically based off of different relation types. So we need to learn a node embedding, an edge embedding. And together with that, we need to learn a projection matrix. So we don't translate relations nodes using vector R in the same space. We use different spaces, different vector spaces, and we learn how to project our nodes into those vector spaces. That's what trans R is. So I have node embedding ZH, I have node embedding ZT, and I learned this projection matrix M tau, which is specific to this edge type, right? So I'm using that M matrix M, I am projecting ZH and ZT into the basically relationship specific vector space for each relation, and then in that basically particular relation specific vector space, I do the translation. So now I formulate that as below. I have the same formulation for essentially our trans C, except that now I have basically projected my matrices, my node embeddings, my entity embeddings into different vector space. So I have here, instead of ZH, I'm translating projection of ZH, and instead of ZT, I am basically comparing it with the projection of ZT, based upon the particular type of edge that I have between these two. So visually, we have these two embeddings here. We project them into some space, and I'm using a basically superscript tau to show that these embeddings are in relational vector space for relation tau. And then I translate these embeddings at that vector space. So now let's see what we can and we cannot represent using trans R. Can we represent symmetry? So if I want to represent symmetry, that means that I can learn a basically vector space in which my embeddings are translated on top of each other, right? So, and then I learn some relation, R tau equal to 0 embedding, that only in this basically particular relation, their embeddings are projected on top of each other. But then again, ZH and ZT are not basically projected on top of, are not on top of each other. So we don't have the same problem that we had with trans E. So can we represent anti-symmetry? Again, yes, we can. Similarly to trans E, we can just learn it in such a way that we have basically these are not on top of each other. So I basically translate ZH tau using R tau to some point that I get Z essentially tau T. And then when I translate this tail node to tail embedding, projection of the tail embedding using relational embedding R tau, I get somewhere that is not my basically projection of my head node embedding. So I'm able to represent anti-symmetry using this as well. Can we represent inverse? So yes, we can represent inverse. So to be able to do that, I need to have essentially, first of all, I need to learn the projection matrices for two type of basically relations that are similar to each other. So I need to first project ZH and ZT to basically same vector space for relationship tau 2 and tau 1. Because if I want to translate, so we can't translate in between the projected vector spaces. We can't translate in between a projection for essentially type tau 1 and type tau 2 unless they're projected on the same vector space. So if I want to be able to represent an inverse, essentially logical pattern using trans R, I should first learn the same essentially projection matrix for both types tau 1 and tau 2, which are inverse of each other. And then in that, we can use just the way we did it using trans E. We have some relational embedding for tau 1, which is negative of the relation, basically a relational embedding for tau 2. And that way we can represent essentially inverse relation between two different entities. Now, the problem with trans R is compositionality. So if I have two, basically a pair of relations that are inverse of each other, we can essentially say that we're projecting them onto the same vector space. But then if we're doing the same thing with compositionality, we should essentially put everything on top of each other, right? So every two pair of edges should be projecting you to the same vector space. So we can't do the same for basically compositionality. And if we don't do that, what we will have is that different, basically we have projected our embeddings, node embeddings into different vector spaces in between which we can't do the translation. So we can do, we can represent this type of logical pattern using trans R. Now, the last approach of this type of basically translational type is called rotate E. And this is the most recent approach. It was published in 2019. And it is based on the idea that, so first of all, it is using a complex space in order to represent the basically node embeddings and relational embeddings. And it is based on the Euler's identity. So using this, what we are saying is that we can represent a essentially unitary complex number using a rotation in the complex space. So if I have an embedding vector whose size is 1, right? Whose basically is 1, right? This vector is size 1. Then I can represent that using a rotation of basically size theta in the counterclockwise direction around the center of our plane. So in order to do that, what we do is that we take our node embedding, the head node embedding, we rotate it according to our edge embedding. We're representing the edge embedding using our tau here. And when I do that, I now compare it with the tail embedding that I want to translate to, right? And what I'm doing here is element-wise rotation. So I'm rotating each element according to the basically angle of its own, right? Our tau is a complex number of dimension d. ZH and ZT are also vectors in the d-dimensional complex space. And that's it. So now, all this said, we would like to see if we can represent different logical patterns using rotate E. So first of all, we're going to look at the symmetry. When we're looking at the symmetry, we see that I want, by performing a dot product, a Hadamard product, between ZH, meaning embedding for the head essentially entity, I should be able to translate it, essentially rotate it using this R tau to get to embedding for tail entity, right? And then I can do the same for the other way around, right? I should be able to start from the tail embedding and then rotate it according to R tau, and I should be able to get to the embedding for the head end, basically, entity. So we can do that. Let's say that in this complex space, our ZT is here. We can rotate it by pi, and we can get to ZH, and we can rotate ZH by pi again, and we can get to ZT, right? So we are able to, if our elements of R tau are equal to -1, for instance, as an example, we are able to represent a symmetric relation where we can, using the same embedding, start from ZT, get to ZH, and start from ZH, get to ZT, right? So next we're gonna look if we can represent anti-symmetric logical patterns here. And we will see that, yes, we can. So this one is similar to the idea that you saw in Trans C. So basically, you have some ZH, you're learning some R tau, just as an example here, it rotates you to ZH here. And then you are learning, you are again, starting from ZH, you are rotating it with the same angle that you rotated ZT, but you're not at ZT anymore. So you're somewhere that is none of them, right? So we can, we started from ZH using the same entity relational embedding, and we got somewhere that is nothing essentially, which is goes with the anti-symmetric problem, basically logical pattern. For inverse again, yes, we can do the inverse. So inverse can be done used by learning conjugate complexes of the embedding that we learned for the basically for one. So the two relational embeddings that we learned should be complex conjugate of each other. And that only means that our real value is the same, but our imaginary part is multiplied by a negative. Last one that I would like to see if it's possible or not is compositionality. In this, what we do is that we say that I should start from ZI, move to ZJ. And that's going to happen with some essentially embedding R tau 1. I'm going to start from ZJ and end at ZK. And that's going to happen with embedding type tau 2, right? So then each of these are represented by some angle, tau, basically theta tau 1 and theta tau 2. If we define a new embedding, which is represented by an angle, which is sum of these two, we would be able to start from ZI and get to ZK. So essentially, the way we can learn compositionality is that we learn some embedding that represents some angle theta 1. And for the second type, we learn some embedding with that rotates with angle theta 2. Our third type of embedding for the relation type 3 should rotate our initial point with angle theta 3, which is sum of theta 1 and theta 2.